All right, we are discussing today the conservation of energy. The idea that energy cannot be created or destroyed, but only transferred. To begin with, let's discuss this in the form of what I'll call not a law, but the conservation of students. Currently in this classroom, there are 16 of you. Okay, if I decided to walk out this classroom and not walk back in again, yeah, Spain hour's not teaching today, not going to happen, but let's pretend for a second. I walk out there's 16 of you in here, and at the end of class, the bell rings, and I count how many people leave. If I count 15, what's the most logical thought then about that 16th person? They are still in the classroom. It would not make sense to have the thought, oh, they've been destroyed. Yes, that would be ridiculous. Or, let's try this. I count 16 people in here, I walk outside the classroom and I leave, and I count people accurately, and I get 17. What is a logical thought? You think someone was, that's the most logical thought, that someone was created inside the classroom? The middle of a physics classroom seems a bad place to be created. Yeah, probably they were hidden in here, or they snuck into the other classroom, or something along those lines. So your first thought is not that a student is created or destroyed, but simply they've come from somewhere else. This is a basic rule of conservation. All the number at the beginning, what do you expect about that 16? Okay, if I count in the beginning and 16, what do we expect at the end? 16. If you don't get 16, it means you're not looking in the right spot for that 16th person. Make sense? Cool beans. All right, that's conservation of energy in a nutshell. Now, to give a more bearing to this scientifically, let's combine two ideas together. An example of work kinetic energy that we've used essentially 1,000 times already, along with conservational stuff that we did on Friday. Actually, before we do that, I'll come back to that in just a second. This is the tree that we dealt with on Friday, yes? Let's practice with it real quick. Okay, I'll give you a type of energy it starts with and a type of energy it ends with, and you see if you can't tell me just a situation that would go to kind of the reverse of what I gave you on Friday. All right, electrical to light. Start easy here. Yes, should be relatively simple there. A light bulb, okay? Any others? Think of another one. There's a lot of them. What else could you do? What's that? I don't think you don't know. Is it? What do you mean? What sparks? What's that? Your phone? Yes, your phone would technically work in that case. Or if you ran enough current through a wire that it started glowing, because you put too much electricity through that wire, that would work as well. All right. What about electrical to sound? Speaker. Fair enough. Okay. Let's go easy one. Thermal to light. Anything hot, right? Really doesn't even have to be a hot fire. Put a bunch of energy into a piece of iron. Eventually it's going to glow, right? Because its temperature is going up in that particular way. Okay, chemical to sound. There's a whole host of answers here. What's that? Vocal cords. Yeah, me talking to you right now. What else? What's that? You're right there, giving you.
Crackling of a fire.
Okay, crackling of a fire, but you're ready to do boom, boom, boom at fireworks. Absolutely, you could do fireworks, or that by that expression, explosions. Okay, any bomb, pretty much whatsoever. Okay, how about this? Chemical to kinetic.
What?
Chemical to kinetic.
Moving.
Thank you for the demonstration. I wouldn't have got it if you hadn't have done this along with it. Yes, just moving around. A human being moving from place to place, which connects me back to the example that I was looking for at the very beginning that I've done a bunch for the work-net kinetic energy theorem. It's me walking around the room. Now be careful with this. Be very careful. As I am walking around the room at a steady pace, if we go over here to conservation of energy, what type of energy is turning into what type of energy? Be careful. What's it starting off as? Chemical is correct. To what? No. Why is it weird I didn't say kinetic? Thermal is the correct answer. Okay, let's talk about why it's not kinetic when it is kinetic and get specific. Okay, so here I am standing here. Okay, in order to get going here at the very beginning, of course, what would I do with the force diagram? What would my force diagram be when I take off? Gravity, sure. Normal, sure. Well, hold on a second. I'm taking off.
Force, muscles.
Let's go random force. So yeah, legs on person in this particular case. And why would there not be much friction at the very beginning? As I said, I'm taking off. Now, in this particular case, what would you expect with the work kinetic energy theorem? Is work being done to the person? Yes, work would be being done to the person in total. Would work net being done to the person? Yes, it would. There's only one. How many forces up here are going to be doing work? One. So, how is there work net? Yes, if there's only one, there's got to be work net. So, would you change kinetic energy? At the very beginning. Yes, but usually when we talk about this, we talk about me walking around right now. What's different about the force diagram as I'm walking around right now? It's constant because there is a force now that we said wasn't there a second ago. Yep, there's going to be friction. And how is friction going to relate? Why is it going to be equal? Because I'm not accelerating. Cool. So there's my force diagram. If we looked at this in terms of work kinetic energy, I said something, I've done this one a bunch of times in here, so I'm not going to spend a ton of time on it. I say I put in 3 calories of work, or something like 12,600 joules, because there's 4,200 joules in 1 calorie. Of course, this would be over some particular distance. Why is my kinetic energy not going up? Because friction's going to do what? It's going to be the exact same size because of the diagram. Am I going to go to the exact same distance? Yes. And the angle is going to be 180. So how much work is friction going to do? Negative 12,600 joules. So in that, we would say, is there work being done? Yes. Is there a work net being done? No. So is there any change in kinetic energy? No. But as we come over here, am I still putting chemical energy in? Yes, I'm putting in 12,600 joules. Okay? So why is it going over here to thermal? Well, let me explain using this, connecting into conservation of energy. What really matters here, it's going to help us to understand this, is Newton's third law. What's Newton's third law?
I love that.
Mixed and matched. You had some right words in there. They might not have been in the right order, but you were very confident. I love it. For every force, there is an equal and opposite force in the opposite direction. All right. So here's the force of legs on Spanauer, and there's the force of friction. Which friction would this probably be? Would that be air or surface that's primarily stopping me as I walk across the front? Air, correct. In other words, what's happening is there's electrons on the outside of air, and there's electrons on the outside of my face, and those electrons are pushing my face this way, despite the fact that I'm going that way, doing negative work on me. Yes? So that's the force of air on face. Spanauer, if you want, a person. Okay. Air on person. Third law says, what does there have to be? Force of person on air. So it's pushing me that way, but let's now focus on the air. I'm pushing it this way. Am I pushing it the exact same force that it's pushing me? Yes, because that's Newton's third. Am I pushing it the exact same distance that it's pushing me? Yes. Because if I walk 8 meters, how much am I going to push how far am I going to push the air?
8 meters.
8 meters. So in other words, it took 12,600 joules out of me because where does that positive 12,600 joules go? Into the air. And how do we see more kinetic energy in the air manifest? As thermal energy. So 12,600 joules of energy came in through chemical right here. Even though I lost 12,600 joules, but conservation of energy says you don't lose 12,600 joules of energy. It doesn't disappear. It just goes somewhere else in that particular process. How are we doing? Cool. So ultimately what we're going to see today is this. We're just going to do what I just did with students earlier. Conservation of students is add all the students up at the beginning, add all the students up at the end, and if you've done things right, what should you find? The numbers are the same. So here is the law of conservation of energy. Here's its mathematical equation. Add all the energy up at the beginning, add all the energy up at the end, and we should find that those two numbers are equal. And before we get much further, some of you might have noticed if you've got ahead to 5.4, I know not all of you have, but if you've got ahead to 5.4, there are some equations that are missing, so we do need to discuss those very quickly. It's the equation for those two guys right there. There are 9 types of energy up here. We are not going to create equations for all 9. If you want to deal with the non-mechanical, you're really curious about the non-mechanical, I will tell you that that one is mostly Chem 2, but a little bit us. That one's a little bit Chem 2 and probably more so us. And those bottom 4 right down there are coming in Physics 2. I say us, I'm sorry, Physics 2 is where we're going to discuss those particular ideas. Okay? But we, right now, in this class, are going to focus on all of the mechanical energies, which, if you'll remember, the other way to say mechanical energy is the sum of all the kinetics and all the potentials. Well, we have an equation for this kinetic. We don't have an equation for potentials, so that's what we're going to work on right now. Let's start with gravity. Let's start with the word potential. This is the potential to do what?
Possibility of work.
Possibility of work. So all of these equations have to start with work. What's the equation for work?
I was not ready for that.
Force gravity times delta x, or sorry, yeah, cosine theta.
Okay. Or technically, we could also use what other equation? Force parallel to displacement. Somebody asked me last hour, by the way, this is a good quick aside. I had a problem like this where I said, okay, there's a hill that's 20 degrees. We just did a practice problem at the very beginning. We don't have to keep doing this if you don't want. But he said he was looking at some homework problems from other people doing this, and they were using sine. And I said, yeah, that's completely okay. And they go, wait a minute, you haven't used sine in the slightest here. And the answer is yes, because if you remember, the whole goal of cosine is to make sure that these two are parallel. Yes? So if you go down the hill, let's go, here you're going down the hill, and gravity points this way. Where did we see your angle needs to be measured from? Where does your angle need it from where to where? Displacement to force, aka it would be this guy. So if this was your problem, what should the angle be? It should be 70 degrees. Yes, not the 20 that was given to you. Too often people just grab that 20 because they see a 20, they see an angle. I'm just going to throw it straight into the problem without checking. No, it does in fact need to be 70. So you might say, okay, why does that need to be the angle? Well, let's just make this delta x. What do we care about? What we care about is how much delta x is parallel. If the angle is here, which part of the triangle is this guy? Adjacent, opposite, or hypotenuse. If the angle is here, this is the adjacent, which is why if the angle is there, the adjacent will allow us to go cosine in that particular case. But if you measure the angle over here, or you want to leave it there, which part of the triangle is this over here? Opposite. And the math works out that the cosine of 70 degrees is 100% equal to the sine of 20. To which somebody correctly asked me last hour, oh, Spainhour, then can I do this? And I told them, I said, yes, 100% you can. I have no issue with it whatsoever, except I will say this. Having taught this class as long as I have, I can almost guarantee you that if you are struggling to figure out the correct angle here, where you only have to change one thing, being allowed to change 2 possible things is going to result in more mistakes more often than just having to change the one up here. Totally your call, don't care, but that has been my experience as I continue forward. So I say all that to then say, going back to this example, let's look at this. Let's look at, okay, here I have a ball. Okay? We're trying to figure out how much work gravity can do. So let's say in one situation, I drop the ball straight to the ground. And the other one, I pop it a little bit to the horizontal, and so it goes through projectile motion in situation number 2. And then I pop it even more So it goes over here. And in the third example, I don't even let gravity take over. I just grab the ball myself and I go all over the witch case, okay, kind of around, and I end also on the ground in that particular case. Do all four of those have the same displacement? Even if you're not worrying about the distance, I'm not asking do they have the same distance. I am asking displacement. Even still, the answer is no. They don't all have the same displacement. Are all of those? Are you going to have an okay time finding out the angle for all three of these or all four of these situations? Probably not. Okay, it's not going to be super easy to use this. But do we actually care about these things? No. Just like the problem we did at the beginning of Friday, what we care about is how much displacement is parallel to the force. Do all four of these situations have the exact same amount of displacement parallel to the force? Well, which way is the force going? Down. Do all of them start at the same y and pretty much end at the exact same y? So do all of them have the same displacement? So in this case, gravity should do the exact same amount of work on all four of them. And the amount of work that it's going to do is going to be force. How do you calculate force of gravity? mg. Times the displacement that's parallel. If only I had a name for the displacement parallel or the distance up and down. Some people might say that they could make fun of me because my distance up and down isn't as tall as, say, an average male's. What name do we already have for a distance up and down? Height. So why do I write height? Is that not the displacement that's parallel to the force since we're dealing with gravity? Yes. So here's my new equation. The potential energy of gravity is equal to mgh. Now there are some tricks to this. Let's go ahead and put this on the other slide real quick. I'll come back to that, by the way, in case you still needed it. Here's the equation. When does that equation say you'll have no potential gravity? When does that equation say you'll have no gravity? When you don't have any height. You could say no mass, but if you had no mass, then you probably aren't asking whether or not it's, here's no mass. Does it have potential of gravity? Yeah, probably not. Gravity's going to be constant, so it is simply the height. So here's a tricky situation to deal with. Do these have the same amount of potential energy? Okay. Which one has more potential energy now? Fluid. Which one has more potential energy now? Okay, why do you say that? So where is the zero then for this situation? Not necessarily. Because you want to keep things consistent. Ultimately, the answer to this is you get to decide. Because watch here. Do those have potential energy of gravity? You'd say no, except if I Wile E. Coyote this beast and cut a hole in the ground, you'll remember we're on the third floor. Do these have potential energy of gravity? It's all a relative conversation, okay? Meaning you get to decide where the zero is, and we're going to see this in homework problems where things get a little bit challenging, but does that have no potential energy? Totally up to you. Totally up to you. Okay, now watch this. Let's say this guy right here, I'm just going to make up some numbers so we're doing this quick with me, okay? Let's say this is 1 joule, okay? 1 joule if that's 0. Does it still have 1 joule? Yes, if I make this my 0. But where's probably the more logical place to make the 0? The ground. Okay, so let's say, why would this, in that equation, have less gravitational energy than this one? Well, if you move the 0, what did you also change? You increase the height. Correct. You change the corresponding height. And that's the answer to the question. How do I move the 0? You change the heights correspondingly. It is okay to leave the 0 here. You go, whoa, what does that mean happened then as it dropped on the ground? Gravitational energies can go negative. And the reason it's okay is this. Making up some numbers here real quick. Let's say I do the heights and I say that that's like, I don't know, 60 centimeters, and I had it 20 centimeters up here. Well, if that's 1 joule, then it's currently sitting at -3. How much did it change? No, total from 1 to negative 3, it would have changed by 4. Well, if I take it and I move it over here and I make the ground 0, that's fine to make the ground 0, but now it's sitting at 4. So is going from 4 to 0 the same thing as going from positive 1 to negative 3? That's why it's completely okay. How will this manifest in problems? Let me show you real quick. Either today or tomorrow, probably tomorrow because it's not easy. I almost wrote it on the board. I'm recording for people online. My apologies, people online who didn't quite get that conversation. Okay, we'll do a problem where both of my sisters went to Uganda when they were in college, and they both bungee jumped over the Nile. It's a weird brag because it's my sisters and not me. But anyway, they jump off of here and they land probably something like 5 meters above the water. Where are most people probably going to put 0? Probably the water. They would say 0 energy is there. But then I asked the question, okay, if you did that, where they started, do they have potential energy of gravity? Yes. Where they end, do they have potential energy of gravity? Yes, they had it in both spots. But you put the 0. Couldn't you put the 0 here? Yes. 100%. Now you say, do they have potential energy of gravity up here? Not as much. Correct, yes. Why is it not as much anymore? Because the heights are different since I'm measuring from a different spot. Would they have potential of gravity here? No, which makes the math a little bit nicer because you don't got to calculate it anymore. Totally up to you. All right, next. I said there was 2 types of energy we need to look at. What do we need to look at now? Elastic. Now, what did I associate elastic with? Springs, correct. So let's draw a spring on the board. So here's a mass horizontally sitting at equilibrium. How much force spring is on there right now? 0, correct. And how would I put force spring into that spring? How would I need to get force spring? Push it or stretch it. Which one do you want me to do?
Just do
Compression, so I'm going to push it inward. Fair enough.
I said push.
Push it in?
Yeah.
Hold on. Okay, fair enough. So there it goes. So pushing in. By the way, real quick, what is the equation for force spring?
K times delta F.
All right. To which you might point out correctly that, yes, it is associated with a spring, but Spainhour, you said elastic could be a lot of different things that aren't springs. 100% true. A rubber band can be associated with elastic. A bungee cord can be associated with elastic. I mentioned that your face could be associated with elastic and wants to return to its original position. And all we do in those scenarios is say we know they're not springs, but we can actually still basically treat them like springs. Okay? If your face gets pushed in twice the distance, does it push back twice as hard? Yes. So as a matter of fact, your face in this case, is a spring. All right. Now, in this case, you've got this stretched out. And at this time, where I've put it in, oh, by the way, how did you say you would have made this happen? And what energy do you use? What type of energy do you use? Chemical. So this is actually that scenario that you just dealt with is chemical into potential. Well, we don't say potential in here. Remember, there's that whole kind of conversation. Elastic, yes, in this particular case. So now I've got it sitting here, and which way is there a force on this guy? Don't worry about gravity and normal right now. To the right. There's force spring to the right. And how do we calculate it? Well, that's K delta X. And what is delta X, by the way? Guys, I get it's the end of the day. I know it's challenging. Here's my issue, okay? I look out and I see your faces annoyed, and I get it. Totally not my fault, though, and I got to look at your faces. So appreciate the fact that you're annoyed. It's the end of the day. You're tired, and this is hard. That's all fair. I'm also with you. As a matter of fact, worse for me, this is my 5th time teaching physics today. I'm also tired and annoyed. But you don't see that look on my face. If you don't want to see that look on my face every time you ask me a question, please do me just a solid and do your best here to pay attention without the, this is so terrible. Okay? I see it, I get it, I understand it. It's fine. We're going to deal with 6-hour physics all year. That's not going to change. So we do have to, and I apologize, this is my best advice for you, suck it up. What's up?
Is the delta X the distance of you compressing it?
Correct. That was already defined by delta X. But what we want right now is potential energy elastic. And that's potential to do. Potential energy is potential to do.
Work.
Possibility to work. How do we calculate work?
Oh gosh, that
F delta X.
Force parallel to displacement. You just saw a second ago, oh, this should be easy. It's not, sadly, but it should be easy. How do we calculate force? K delta X times delta X. Except, here's the problem. That equation right there is assuming that the work is constant. Any of you that tried to skip ahead and do 5.4, I should have warned you, I apologize, I meant to warn you, and it just kind of slipped my mind. Okay, you can't use this equation because of the following thing. Does the force actually stay constant the entire time you're pushing it? No, we said a second ago, what is the force here at the end? 0. And here it's maxed out at K delta X, but it changes the entire time that you're going through this process, yes? So let me show you how we get around this. Well, technically the answer is calculus, but we can avoid it without calculus like this. If I were to graph force spring versus delta X, you actually already know exactly how the shape of that graph should look because you can see it right here. Since force spring is the first power and delta X is the first power, what shape should it make? Linear, which, like we just saw a second ago, has a minimum of 0 and a maximum over here of whatever the heck K delta X is. Yes? Now, you can see from this that it does not stay constant. It is always getting smaller and smaller. But what is staying constant is the average. How do we get the average of something? And if it's linear, really we can just take 2 spots, which we already know. What's the maximum? K delta X. What's the minimum? 0. And divide by 2. So, let me finish this real quick thought. I'm going to be right with you. Okay. Instead of putting K delta X, because K delta X changes, weirdly we can replace this with the force spring average, which is just as easy as taking K delta X and putting 1/2 in front of it here.
You said 0.05 in the email.
And what is 0.05?
Not a half. 0.05?
Did I say 0.0?
Yeah.
I thought I said
I did
0.5.
everything like that and I was freaking out and then I realized you just added a 0.
Positive it said 0. Okay, well, I could be wrong. Anyway,
No.
okay, fine. Fair. Moving on. All right. 1/2. Did you not look in the textbook? Why are you waiting on me on this particular front? All right. Simplifying this all out, what could I do to simplify? Well, that's 2 delta x's, so 1/2 K delta X squared. Now, what does that squared mean? Well, oftentimes in physics, a square doesn't mean anything other than it's a composition of its parts. What does it mean if I take a spring and I stretch it twice as far? Well, because I stretch it twice as far, will I have twice as much force? Yes. Will I also, because of work, have that double force go through double the distance? So what effect will that have on work? Nope. I double the force and I double the distance. Work should go up by 4 times, which is exactly what this equation says right here. If I double my displacement, work should actually go up, or how much energy stored should it go up by 4 times. Where am I at right here? Because I'm realizing I missed something earlier. This also goes to the kinetic energy equation. If you're driving down the road at 30 miles an hour, and you find that there's something in the way that you need to stop for, like a tree. Let's say you want to stop, or a person, sure, I guess if you want to. Okay, you hit the brakes, which apply what force? Friction. Okay, there's other forces as well. Here's normal, here's gravity. But you have a particular speed, which is associated with a particular kinetic energy. You have to apply work in order to change that in energy. That friction would give you a certain amount of distance that you would stop. Yes? If instead of going 30 miles an hour at a particular velocity, say instead your car is going 60 miles an hour, or twice the velocity, what does that mean about your kinetic energy? Look at the equation. Doubling the speed does not double the kinetic energy, but does what? Makes it 4 times as big. So if you now have the exact same brakes and the exact same force friction, which more than likely you haven't switched out your brakes to go 60 miles an hour, and that person gets in front of your particular vehicle or tree, how far does it take for you to stop? Not twice the distance, 4 times the distance in order to stop in that particular case. All right. Now, let's get to the math of this. I said at the beginning that we were going to do conservation of energy. Now, here's technically how that works and how we're going to solve it so that we don't have to do that. How many types of energy did I give you? 9. So technically, to do this right, I got to put 9 initials and 9 finals. Okay, which is annoying, and obviously you don't want to do that, so let's talk for starters why you don't have to. Does this duck have nuclear energy? You're wrong. 100% it does. As a matter of fact, what was required in order to have nuclear energy?
A bomb.
Mass. A nucleus. Mass at all. The original bomb that was dropped on Hiroshima was about half the size, its fuel was about half the size of this right here. After it was done, that mass no longer existed, but came out in the form of energy. So I ask again, does this duck have nuclear energy?
Yes.
Quite a bit. Now, if it ever was worried about releasing it, I wouldn't be at school that day, and I would probably warn all of you because I care about you very deeply or whatever. But if I dropped this duck on the ground, no worries. Okay, no worries. Wasn't going to do it if it was likely to release nuclear energy. Do you expect its nuclear energy changed? No, because its mass didn't change. So why is it unnecessary to write the nuclear energy initial and nuclear energy final mathematically up here? Therefore, what would that do mathematically? It is still there, but they would cancel it out mathematically, telling us, do you have to write all the types of energy on both sides? Only if they change is correct. And on top of that, I'm going to make it one step easier. Instead of the conservation of energy, we are actually going to do the conservation of mechanical energy. Now, the conservation of mechanical energy is not a law, and we'll talk more about that first thing tomorrow. It is an assumption, and assumes that certain things are happening that we regularly assume are not happening. But we'll fix that a little bit more tomorrow. Now, how do you use it? Well, let's use it right now for a situation that was hard but makes this a little bit easier. I have a roller coaster, and we're going to say this starts from rest, and we're going to assume right now it's frictionless. Comes down the hill, and let's say this is 35 meters, and this is 15 meters. And the question is, how fast is the car going at the end? Now, why can I not easily use work net kinetic energy theorem here? You could use it, by the way, but not easily. That was gross.
You don't have an angle?
We don't have an angle. We don't have a lot of stuff. We don't even have mass, right? I didn't give you much of anything, quite frankly. Okay, but let's look at it in terms of conservation of mechanical energy. Now, if you don't know any better, okay, you can just write all the 3 types. What are the 3 types of mechanical energy? Kinetic, gravitational initial, and elastic initial. Okay, and you can do the same for the end. Now, I say if you don't know any better, you can always do this. However, if you do know better, you could have technically not written 2 of these. Which ones and why? Hold off on that, because you're not wrong, but actually you're one step in front of me. What's that? No, don't do that yet. Because again, I think it's a similar reason what she was saying, but not the ones I'm looking for. Yes.
Gravity, because it stays the same.
Again, you guys are all in the same boat here. We're gonna cancel some stuff in a second. That's not what I got you. Okay, never mind. So the reason what I was going for is I would not write either elastics. Why?
Because there's no elastic.
There's no springs, and more importantly, back to the previous comment, these things aren't changing. Okay, so the only mechanical energies you actually have to put in a situation are ones in which they change. Correct. So since elastic isn't, you don't have to do that. Now, for my work, I would still require you to write them, even if you know they're 0. And some of you do have already recognized that some of them up here are in fact 0. And actually, even if they're not 0, you can make them 0. We'll get to that in a second. If they are zeros, I still want you to write them if they change in the situation. So, for example, somebody might have pointed out, what is kinetic initial? 0. I would still want you to write it in the work because it is changing in the problem. Does that make sense? Okay. Now, do any of the others cancel out? This is a sort of a depends situation based on a conversation we had earlier. You could do that. What do you have to do in order to say gravitational final is 0? You have to move your 0. I don't care. Both will work out the same. Here are the two more likely scenarios. One, if you're uncomfortable with that, leave 0 at the ground. And then if I ask the question, is there anything else that cancels? The answer would be no. Or if you would like to move your 0 here, you can, but what change do you need to make? I'll give you a starter and you tell me what it needs to be. Initial height is no longer 35. You would need to change the corresponding heights. What would initial height be then? 20 meters in this case. Does that make sense? Because you're going from, this is my 0 to the top, so 15 by 35. I'm going to do it as though we leave 0 at the ground, because early on that's probably the most likely thing that you would do. And let's go ahead and fill out from here. Okay. How do I calculate potential of gravity initial? How do I calculate potential of gravity initial? MGH. Okay. Again, people go, I don't know mass. Just wait. All right. Equal, what's my equation for kinetic energy? V final squared. And what's my equation for potential energy of gravity final? Final. And right now, masses cancel. Now, do be careful of this. The masses are canceling, okay? But if I ask you to calculate total energy, can the mass cancel then? No. We can only cancel them because we could see that they affect all the energies the exact same way. So we divide by mass, and they cancel. Then what would you do algebraically? More specifically than that. Bing, bang, boom. We got it. A little bit more specific. We're looking for what? Find speed over there at that loop-to-loop.
Subtract GH.
Yep, it's the first one I can do. And I wanted to show you that because I'm going to show you something mathematically real quick that you do not have to do. As a matter of fact, I probably wouldn't, but I'll show you the reason why it doesn't matter where you put your 0. Because right now, those G's are the same, yes? So even though you don't have to, and like I said, I probably wouldn't, you could factor them out. Showing you that the only thing that really matters here is the change in height. Notice, by the way, if we don't move the 0, that's 35 and that's 15. 35 minus 15 is 20. If you do move the 0, then that's 0 and that's 20. The difference still being 20, they'll still result the exact same way. 1/2 mv, sorry, no m on that, I already canceled it. 1/2 v squared, v final squared. What do I need to do now? Once again, make sure you multiply everything by 2 here. So even if you were at where we had just a second ago, even if you were at GHI, do not do this. You will not end up with the right result because everything needs a 2. So either put another 2 over there or multiply everything by 2. And then square root. So we have 2 times G times 35 meters minus 15 meters, square root the whole thing. 20 times 10 is 200, times 2 is 400. Square root of 400 is 22 and change, right? What was it? I'm doing it in my head. Come on, you guys got this. What are you sitting around being lazy for? This is so boring. Yes, when you're not working. It's better. Come on, well, you got this. I know. 19.8. How are we doing? Okay, let's do a little more challenging.
That was enough.
You can suck it up. All right. I have a Nerf gun that I turn on its side and I fire it into the air. Okay? All right. We're going to assume that the ceiling is not in the way, and then it fires up about 4 meters into the air from the end of the gun. The mass of the dart is less than this, but let's just use 50 grams. We're going to assume that this thing stretched, I don't know, 10 centimeters. And I want one more thing. I think there's one more thing. Maybe not. I'll find out. Okay. The question is, what's the spring constant in the gun? We begin right here. And we'll probably pick this up tomorrow. So no worries, if the bell rings, I will stop. Okay. Is the elastic energy going to change? Yes, so I put it on both sides. Is the gravitational energy going to change? Yes, so I put it on both sides. This next one's a little bit tricky, so make sure you're answering the actual question at hand. Will kinetic energy throughout this whole process change? Is it going to change speeds throughout?
Yeah.
Yes, it will. So we're going to put it on both sides. Now, that being said, the next question I'm going to ask before we get too deep into the math is, where are our zeros? Even though kinetic energy is a weird one here, because we got to figure out where my initial and final is. Well, how do I put them? It's where you know. Where would be the best place to put the initial? The bullet starts when it's before it's been sprung. Yes? Correct. So when the bullet's right down here. Okay? So, that being said, once you know the initial, what's kinetic initial? 0. Why is kinetic initial 0? It's not moving at the beginning. Okay, where makes the most sense then to put the final spot? The ground. What's that? Yeah, right at the top. Since I know it hits the top at 4 meters, probably right there. Okay, how fast is it going at the top? 0. Assuming, by the way, I went straight up and down, which we are here, which means both of these are 0. So you might say, but Spain, our kinetic energy didn't change. Okay, but it did change throughout that particular problem. So there we go. All right, we will finish this tomorrow.